In case you missed my comment last class, sections 5 and 6, things will seem a little out of order because I think Stuart has things a little out of order, but we start with this idea from geometry that if you have two rays with a common starting point and some angle between them, you will frequently use the Greek letter theta to describe an angle. We'll use other letters, but that's probably the most common one. No doubt you all recall this idea from geometry that a circle has 360 degrees. That's an arbitrary number. 360 comes, I believe, from the Babylonians. They did not have a very sophisticated way of doing math, and so it was very nice to have a number like this that you can divide by 2 evenly, 3, 4, 5, 6, not 7, 8, 9, 10. You know, this is really convenient, isn't it? You don't get a fraction, not 11. 12 and some other numbers. So that's why we have. It's also why we have 60 minutes in an hour and 60 seconds in a minute. This is not the only scale used for angles. There's a somewhat, unless you're a seaman. Sailor, there's a somewhat obscure system called radians, or grads, in which there are 400 grads in a circle. You really could pick any scale you want. However, some of you will have come across what we're going to talk about here, which I'm going to, without explanation right away, say is kind of a natural way to do this. A radian. There are two equivalent convenient ways to think of a radian. One is you have a circle. It has a radius of 1, and you have some angle. Trying to think of the word from geometry. Sector? No. Is it a sector? Whatever. The distance that the angle intersects, we'll call S, and S is radian. I guess I'm going to use a little s here. I want to use big S. Equivalent, and easy to see, is you take an arbitrary circle some radius r, some angle theta, I guess I should say theta equals s. And now we have big S, and that's not an intended joke here. And theta is equal to big S over r. These are entirely equivalent because these sectors are similar, and the these words just keep escaping me. I guess I have to start shopping for coffee soon. The ratio here, right, 1 to r, just gives us the same angle. Okay, so As a consequence of this, we know that the radius of a circle that has radius 1, the circumference of a circle that has radius 1 is 2 pi. So we have 2 pi radians in a circle. 360 degrees is equivalent to 2 pi. And this is, if you haven't seen this before, you really need to focus. Since we're going to be using radians, you need to know how to convert back and forth. Before we go for that, let's just look at some obvious examples of radian measure that you will need to know. 180 degrees, the number of degrees, sum of the angles of a triangle, that's just going to be pi. A 90-degree angle, a right angle, perpendicular lines, they're going to have angles of radian pi over 2. There are 3 more that are very useful to know. 45 degrees, of course, would be pi over 4. And the other 2 will be 60 degrees and 30 degrees, which will be what? Well, 60 degrees will be pi over 3, and 30 degrees will be pi over 6. So this is just the equivalent radian measure. If you're familiar with degrees, if you're not familiar with radians, again, you want to focus in on this. It's going to be, you're going to see many problems which are going to be in radians. Right. Jumping ahead of myself here. Let's find out how we convert. I mean, maybe we don't have a nice angle that we know. So if we want to convert from degrees to radians, well, let's pick some number, 57 degrees. Okay. Well, we just need a ratio where on one side of the ratio we have an equivalent amount of degrees and an equivalent amount of radians. So your choices are, you could say 2 pi over 360, or maybe a little easier to deal with, pi over 180. If you ever get confused about which way the ratio goes, is it 2 pi on the top and the bottom? Well, you can think of units. We've got degrees on top, we've got degrees on bottom. So they're going to cancel, and we're going to get 57 times 2 pi over 360, or the equivalent. So that's how you would convert degrees to radians. Radians to degrees would be just the opposite. What's 1 radian in degrees? Well, we're going to multiply it by, let's try 180 over pi, which I think is about 57 degrees, something like that. Okay, so that's this new set of measuring that we're going to use. I think we're going to get to this in another class or two, but there's this very deep and embedded reason we use radians. I can't go at it today because we don't have enough information yet. But this is not just some weird number. This is just very fundamental to mathematics. It just makes a lot of mathematics line up in a very beautiful way when we use radians and not degrees. But there are purposes for radians outside of trigonometry. And that comes from its relationship here, where theta equals AS over AR. So let's just see a problem where that would come in. I'll make one up. So I have a ship, and it has an anchor and it has a spool, which is, we'll say, 1 meter. And the anchor is down, I don't know, we'll make it easy numbers, 100 meters. We want to know, well, that's too easy, isn't it? No, it isn't. Okay, so we want to know how many times we have to crank this to bring up the anchor. Well, this 100 meters is going to get wrapped around. So S is 100. The radius is 1. So that tells me how many radians? Angles S over R is just going to be 100 radians. Oh, okay. Now you might say, well, that still doesn't answer my question, because I want to know how many times I'm going to have to crank, but each crank is 2 pi, right? So it's just going to be 100 over 2 pi, or it's like about 15 or 16. So you can just use this idea of radians to solve this kind of problem. All right. This next application isn't really depending on radians at all. You could do it with degrees. You have a sector of a circle. Angle theta equals, in this case, 60 degrees. Yeah, it doesn't really matter. But 60 degrees, so pi over, that's keeping up. Thank you. I guess we'll do it both ways. We want to know the area. Okay, well, the radius is 3 meters. We know that the area of this sector, the ratio of the area of this sector to the whole circle, will be equivalent to the ratio of this angle to the entire circle. So we can either look at that as 60 over 360, or pi over 3 over 2 pi times the radius. I mean, times the area. And the area, of course, is pi r squared. That's 9 pi. That doesn't look like multiplication soon. So we can find the area of a sector of a circle using that ratio. These are all kinds of problems that you'll run into in the homework. All right. All right. So that's step 1, radian measure. I want to take a deep breath after that, because we're going to start using radians in a particular way. You can also use degrees in this manner too. We're going to define something called, I want to write it down first. Called an angle in standard position. So what do I mean by that? Well, I take an XY set of xy axes. One of my rays, my angle, starts at the origin and goes out from x. And the other ray is wherever it is. And this is what we call an angle theta in standard position. You know, angles can, they could be in any direction, but this is just a specific definition. Now, we're going to do something here that hopefully isn't new to many of you. If you've only done triangle geometry, you might find this new, right? Because we're going to extend this idea of an angle so it's not limited to 0 to 90 degrees anymore, or even 0 to 180 degrees, right? We're just going to say we start here and our angle can go around as many times as we want. As far as we want. And we have a name for this. I don't think we have a name for this. I'm going to call this a directed angle because very specifically we're measuring in a counterclockwise manner as a positive direction. Now, if we had an angle down here, we could go all the way around and it would be a positive angle. But we can also go in a negative direction and have an equivalent angle. That is to say, any angle can have many different names. In particular, if I have some angle theta, it's equivalent to any angle theta plus 2 pi n, where n is an integer. So we can subtract 2 pi or add 2 pi. All these angles are equivalent. We have a name for two angles that are equivalent in this manner. We call them coterminal. This is a little terminology. I may use it again. It's not crucial. So, I guess I should kind of draw what I'm talking about here. If I have an angle, let's say, of 45 degrees, and if I have another angle, which is, we're going to go clockwise. So this is 315 degrees, minus 315 degrees. These are coterminal angles. They're equivalent. And we can see that because minus 315 plus 360, hopefully I did my addition right, should be 45 degrees. We're dealing with this now because we're going to start talking about trigonometric functions which are applied to angles either in degrees or radians. I think I'm going to repeat something I kind of hammered on last class. Just I'm sure there's at least one or two students who missed that class. When you're using your calculator, when you're using the sine, cosine, tangent for their inverse functions, which you get using the second key, do yourself a favor before you do your first calculation. Check in the mode Long button. Checking the mode. Third line down will tell you, is this calculator in radian mode or degree mode? I can't emphasize that enough because I can't tell you how many times I've gotten wrong answers for exactly that reason. You can figure it out and I'll write on the exam mode, but in the real world you don't want to make that kind of mistake. Okay. Any questions on angle measure? I think most of you have seen most of this before, so I'm going through it a little faster than I would like. But, okay. Take a breather here. It's an interlude, let me catch up with a little point. I did not get any time the last 2 days to work on your exams. I will shoot myself if I don't have them all corrected by the end of the weekend for you. They should all be online as soon as I get it. Well, you know, that's hyperbole. Hyperbola? Hyperbole. Hyperbole. No, I don't do that. Actually, I shouldn't say things like that. You know, every once in a while there's like something like this comes up and then, you know, a student, you know, goes to the dean and says, I'm worried about Mr. Schoenbrun who's sending my... No, I'm not going to do that. So, oh, and don't go to the dean, please, because I'll get phone calls and rate will be cold and it won't be fun for anybody. All right. Okay, so now we're going to go back to trig functions and we're going to start over. On Tuesday we talked about triangle trigonometry. We talked about SOHCAHTOA, sines, cosines, tangents. We're going to redo this now. This is section, and I don't know why the book does it in this weird order. We call this the unit circle view. And I'm just going to read trigonometry. So the idea is, instead of using right triangles to define sines and cosines, which limits them. It limits them to from 0 to 90 degrees, because that's the largest angle you can have with a right triangle. Where instead, we're going to start with a unit circle. This is a circle with the equation x squared plus y squared equals 1, has radius 1. And we're going to define a function in terms of an angle in standard position. And where that angle intersects the circle, there's a point. There's an xy point. An xy point on this circle. We define the functions cosine of theta and sine of theta as the x and y coordinates. Right, we have an x coordinate here and a y coordinate. Now this gives us a big advantage here, because now as the angle moves around, the point moves around, but it always has coordinates. And that's how we define that function. We continue to define the tangent function as the sine function over the cosine function. And we'll get to the other three functions later, later today or later in the class. All right. So there's some useful information we're going to get out of this idea. We're going to go back to this idea that there are four quadrants on the plane. And we're going to look at the values of the sine and cosine in each quadrant. Now, I think it should be pretty obvious that in the first quadrant, both the sine and cosine are going to be positive. And that corresponds with what we saw for triangle trigonometry. The sines and cosines we found are always positive. However, when we get over here to the second quadrant, what happens? The x-coordinate is now negative, but the y-coordinate is still positive. So in the second quadrant, our cosine is going to be negative. I'm sorry, do I have this right? Yeah, that's the x. Yeah, the cosine is going to be negative, and the sine is going to be positive. When we get down here into the third quadrant, they're both going to be negative. And when we're in the fourth quadrant, you'll see just the opposite of the second quadrant. The cosine will be positive, and the sine will be negative. Remember, it's just the coordinate of this point. Not every point is in a quadrant, though. We have the points that are intersecting the axes. So it would be good to take a look at those particular points. How do I want to draw this chart? I guess I want degrees. Degrees theta, sine theta, cosine theta. Okay. So we can have something new on a circle. We can have an angle of 0 degrees. It's simply an angle that goes nowhere. So what do we know about that angle? Well, its sine is the y-coordinate, which is 0. Its cosine is now the x-coordinate, which is 1. Hold that in your head for a second, because it'll go fast from here. Again, we're just looking at the coordinates of this point. Okay, what about 90 degrees? I guess I want to write 0 radians pi over 2 radians. Probably worth repeating these. Well, 90 degrees is now this point up here. And the coordinates have just switched, right? Now the sine is 1, that's the y-coordinate, and the cosine is 0. Moving over 180 degrees, in other words, an angle, which is just straight angle. Well, what happens? It's pi, degrees. The sine now is what? Someone take a look and tell me what the sine, what happens to the sine? It starts at 0, goes to 1. What happens when it comes back to 180?
0.
It's 0. What's happened to the x-coordinate now, right? 180. It's not 1.
It's negative.
It's negative 1, thank you. And similarly, when we come around to 270, again, our cosine is going to be 0 because that's the x-coordinate. But our y-coordinate is now minus 1. This is 270 degrees. This is 3 pi over 2. And we can just to complete things, we have an angle of 2 pi, which is equivalent to 0, 360 degrees. We're just back to 0 and 1 again. So these are, these are important sines and cosines. You don't have to have them memorized. You just have to be able to, work through quickly. Oh, what's the sine of 0? What's the cosine? Oh, right. Coordinate. Oh, it's 1. So you're gonna need these for this course and for the next course. And if you do anything with math that uses trigonometry, you'll need them later on. Okay. That's a lot. I'm going to take a deep breath here. This is out of sequence. We're going to look at graphs of these functions later. But it's useful. I think I've been occasionally drawing a picture of the sine function. So this is pi. This is 2 pi. 0. This is 1. This is minus 1. And it might be useful to take a look at this chart in terms of this diagram. We start here, the sine is 0. When we get up to pi over 2, it gets to 1. When we get back to pi, it's back to 0 again. All right, we can keep going. Now at 3 pi over 2, it's now minus 1. And of course, when we go back to 2 pi, it's 0 again. The same kind of view of things happens for the cosine. This is 2 pi, this is 9 pi over 2. Pi over 2, where you can see the same kind of connection. So we're going to look at graphs later, so you don't have to really focus on that very much today. All right. Now, it's funny how, technology has, in the last, I would say, 50 years, has interfered a lot with some of the common sense curriculum we've had in mathematics. The next subject we're going to talk about is something called a reference angle. And a reference angle makes a huge amount of sense if you don't have a calculator. Because instead of a calculator, you're going to have a set of tables. And the set of tables are not going to give you the trig functions for every possible angle. They're only going to give you the trig functions for a very limited number of angles. So, having said that, let me introduce this idea of a reference angle. It's still an important idea. It has other functions other than, knowing how to look up trig functions in a trig table. But it doesn't kind of logically fit in as well as it used to. So first let me define a reference angle. A reference angle is some angle greater than or equal to 0. And I want to get this greater than or equal to 0, less than or equal to 90 degrees, or pi over 2. Now, let's say I had a table. I wanted to create a table of these reference angles. Before I get to work on it, I might want to note something. If I have a right triangle, and so it's got a hypotenuse, adjacent, opposite. Someone tell me what this co-angle is?
Which one?
This one here. Let's call that alpha. Alpha is equal to, this is 90 degrees, or pi over 2. What's this angle here? This is theta. Sorry?
60.
I'm not hearing you.
He said 60.
60. Well, I didn't say this was 30, so you can't know that. Yeah.
Oh, like the hypotenuse divided by the vertical line.
You're thinking of a trig function, right?
Yeah.
Now, I'm just looking for an angle. This is actually easier than you're making out, Zen.
Oh, an acute angle? An acute angle?
It is an acute angle, yes, correct. But I want to know what exactly its value.
90 minus theta.
Everybody, think about that for just a second. The sum of these angles is 90. So if this is theta, this is 90 minus theta, okay? Everybody got that? It's pretty, yeah, it's not that. Okay, so let's just look at something here. If I look at the sine of theta, what's the sine of theta? That's the opposite over the hypotenuse. Now, what I want you to do is, you don't have to actually turn your head, but just imagine we tip this over. So now this is the angle we're looking at. What is opposite over hypotenuse? That's the adjacent over the hypotenuse. So that's the cosine. What's our angle? 90 minus theta. Likewise, the cosine of theta, that'll be adjacent over the hypotenuse for our triangle, but sideways will be the other one. Adjacent to the hypotenuse. Okay, so remember what we wanted to do is we wanted to have a table for all these. We don't really need a table for all of them. If we have all the sines from 0 to 45 degrees, that's the cosine of 90 degrees to 45 degrees. So if I have all the sines from 0 to 45 degrees, I already have the cosines from 45 to 90. And likewise, if I have the cosines from 0 to 45, well, then I have the sines from, I'm just going to write it this way, 45 to 90. That's great. That means, since I don't have a calculator, remember, we're diving back into the past, to figure out, I don't have to figure out all 90, I don't have to figure out all the trig values, trig function values from 0 to 90. I only need to go from 0 to 45 because I can just kind of switch my table around and I can get the other ones. All right. And so I said our reference angle is from 0 to 90, but just to be clear, anything greater than 45, I'll be able to find its trig functions without knowing them. I'll be able to look at the trig functions from 0 to 45 to figure it out. All right. We're going to get back to this reference angle idea. I'm going to draw a different angle here. And I'm going to put back my circle. So I have some theta here. I have the cosine theta and sine theta is my coordinates. I'm going to draw a line parallel to the x-axis through this point. And I'm going to see where it intersects with the circle here. So now I have another angle. Now, can anyone tell me this angle is? This angle is theta, right? This is 180 degrees. So what's this angle here? Got to do a little geometry thinking here. I mean, keep in mind, this angle here will also be theta, right? So what's this angle here?
Oh.
Is it just 180 minus theta?
Just 180 minus theta. However, think of the coordinates. What's the y-coordinate? The y-coordinate here is sine theta. The y-coordinate here is sine theta. What's the x-coordinate? Negative cosine theta. Aha, that knowing about the sines and the quadrants is suddenly helpful. I know the sine cosine and sine of this angle. Now there's an angle out here in the second quadrant I can figure out. All right. Let's push this a little further. I'm going to extend this line, this vector, well, this ray, into a line. So now, this angle is theta. Question is, oh, I need another color, don't I? What is this angle? Well, this is 270, right?
And then it's,
270 minus theta.
wait, are
Yeah,
they,
it is 270 minus theta.
but they're both negative?
Hmm?
Both sides are negative?
Oh, you're jumping ahead, thank
Oh,
you.
sorry.
It's okay. I have one more thing I wanted to point out. This is 270 minus theta, but remember, these things are they're not unique, right? There are other ways to think about them. So, for example, I could think of it as theta, this is a straight line plus 180, right? It's probably, these are the same, right? Because well, they are. Well, you don't have to worry about that. Okay, so now,
Both of them are negative?
both of them are negative, so I know that this is negative cosine of theta, and this is negative sine of theta. Minus, minus. Now, it's going to be really useful to know about the signs in each quadrant. All right, and finally, if we were to extend all the way over here, have another? I don't know if this is visible, this is blue. Okay, so now we go all the way around. Probably would be just convenient to call this 360 minus theta. Well, what do we know about its coordinates? It's going to kind of be the opposite of the sine, so I have to watch when I use the word sine. There's sine, GH, and SIN, right? So this is the cosine of theta and minus the sine of theta. Okay, so now let's presume we have some values for the sine and the cosine. We also have the values of 4 other angles. We also have the sines and cosines of an infinite number of angles because we can always add 2 pi or radians at 360 degrees. But just within this circle, there are 4 different angles that we can interchange just by getting the SIGN sign correct. All right. Now that's kind of what a reference angle is about. You have some angle in the circle. There's some angle from 0 to 90 whose sine and cosine are equal within, they're positive. These might be negative, 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 positive. But if you just have a table from 0 to 90, you can just look that up, and then based on where you are in the circle, you can figure out the SIGN sign. That's what this reference angle idea is about. So let's well, that's pretty. That wasn't Australia calling, that was it? Let's kind of work this backwards and see how we would use this. Well, any angle that's between 0 and 90 degrees is its own reference angle. So just as a thought experiment, figure that we have some table here. It's got the sines and cosines. And we already told you only need between 0 and 45, or 0 and pi over 4, but Okay. But these are all positive numbers, right? Well, what do we do about, we have an angle in the second quadrant. And I want to draw my circle here. Well, this is some angle, I guess we have to call it theta. It's between, this theta is between 90 and 180 degrees. Or pi over 2 and pi. So now we want to find our reference angle. And call this alpha. Well, this alpha is the same as this. So our reference angle, for this theta, I guess I'm going to call that alpha, is 180 minus theta. In other words, if you take a look at this angle, we subtract it from 180, we get this angle, the reference angle. Now we can look up the sines and cosines. But we just have to make one correction, which is that the cosine is negative. We'll take a break, we'll finish this up, we'll see how you can find the reference angles for every other possible angle. Right. Take 5 minutes, I'm going to do it. I'm going to take a break myself. You should expect that when you're done, that you're going to know how to fill in this chart without aid of calculator. This includes all the angles that are multiples of 30. See if I can make this look plausible. Okay, that's 45, that's 30, that's 60. That's 30, 45, 60, 90. But then we need 120, 135. Guess I have it written down, 150, 270, and so forth. Hopefully you're going to know how to fill in this table using this idea of a reference angle and using the special triangles we've talked about a few times, 30, 60, 90 triangle. And the 45, 45 right isosceles triangle. So let's start with the easy ones. So if anyone wants to jump in, go ahead. The sine of 0 is, this is a good thing to know. Sine of 0 is, you know, like 1 plus 1 is 2. The sine of 0 is 0. Okay, good. And that being the case, the cosine has to be 1. Okay, 30 degrees. Let's look at a 30, 60, 90 triangle. There's the 60 degree. We'll make the hypotenuse 1. The shorter leg is a half. And so the longer leg is the shorter leg times the square root of 3 over 2. Okay, so the sine is the opposite hypotenuse. It's 1/2. The cosine, that's the adjacent over the hypotenuse. So square root of 3 over 2. All right. These aren't too hard. 45, right, isosceles triangle. The hypotenuse is 1. Helps to know that the sides are both 1 over the square root of 2. You can figure that out with the Pythagorean theorem, but if you square this, you get 1/2, you square this, you get 1/2, 1/2 plus 1/2 is this squared. So, okay, so the sine is 1 over the square root of 2. 1 over the square root of 2. And now, you could go through the same process I did with the 60-degree angle, but what's going to happen here, the cosine and sine are just going to switch. This is going to be square root of 3 over 2, and this is going to be 1/2. So the first part of the table, you should know how to fill this in. In a way, that's the hard part. So now we're going to look over here, right? We're going to look at the second quadrant. We know this quadrant, sines and cosines are positive. But this quadrant, the x-coordinate becomes negative, and the y is positive, which is to say the cosine is what's going to be negative, right? I'm missing something here. Well, okay, I guess we did these before, so the sine here is what? The sine is the y-coordinate, so that's 1, and the cosine is 0. Now we want to look at the reference angle for 120 degrees. Okay? So you may recall this angle is 120 degrees. This is theta. That's going to be the reference angle, right? That's going to be 60 degrees, right? That's, angle in the first quadrant, which has positive sines and cosines. So we could just look that up. That's square root of 3 over 2 1/2. But one of the signs is SIGNs is different, right? The cosine is going to be 1/2. Negative is going to be negative 1/2. 45 degrees, really easy. 135 degrees, really easy. The reference angle here, this is 135. This is now 45. So both of these are 1 over the square root of 2. But the cosine is now negative. Anyone want to guess at 150? It's kind of a pattern here you can kind of see coming. Well, all right. Its reference angle is, this is 150, this is going to be 30 degrees. We can just look over here at 30 degrees, 1/2 square root of 3 over 2, but of course, cosine is negative. I want to stop for a second. I want everybody to look at that and think about it. Think about if you have a question, how I got into that. Because you're going to need to be able to do this. you're going to be able to figure out these specific sines and cosines of these specific angles just with pen and, paper. All right, we didn't talk about the third quadrant yet. How you get its, I guess we don't need these anymore. How do we get its reference angle? We have some angle over here, theta. This angle here is its reference angle. Right? So what did we say? How do we get from this angle to this angle? I'll start here from 210. What do we have to do to 210 to find its reference angle? It's in the third quadrant. What do we do in the third quadrant here? You want to think this out because if you just memorize a bunch of rules, you may not remember them. But if you look at it, think about this. Again, this is our angle. This is going to be the reference angle here. What value is that with respect to theta? I mean, this is kind of basic geometry here. You want to see that?
Is it just 60? Is it just 60?
Well, I haven't said what this angle is. It's theta, all right? Don't. I mean, maybe that's where we're going. Oh, you mean here it's 60. Yeah. Well, all right. That's out of that. It's 210 minus 180. Oh, it's 30. So the reference angle is 30 degrees. So we look over here at 30 degrees. 1/2 square root of 3 over 2. But something happens to the signs in the third quadrant, right? They're both minus. So these become minus. I skipped this. I guess we did these before. 180, that's just this point out here. So what do we get? We're going to get the sign's going to go back to 0 and it's going to go b minus 1. This should be kind of easy now. Of course, it has to be 1 over the square root of 2 and 1 over the square root of 2, but they're both negative. And this angle, its reference angle, is going to be complementary to this angle's reference. This was 30, so this is going to be 60. So we just have to look here, the square root of 3 over 2, 1/2, but both with minus signs. And the rest should just fall into place here. This is going to be negative 1, 0. Let's cheat here, 1 over the square root of 2, 1 over the square root of 2. The signs are going to be negative, the cosines are going to be positive. And these are just going to switch again. And we're going to switch over here. Okay, so there's some mental energy that will go into figuring out how to do this. I suggest you kind of take the time as a personal exercise figure this out for yourself. This will help you a lot in understanding reference angles, what the SIGN is for each quadrant, each of these functions. Now, there is one more piece to this puzzle, which is what happens if you have something like this. What is the sine of 765 degrees? We want to find the reference angle. Well, the first thing we want to do is kind of transform this so that this angle is between 0 and 360 degrees. Right? So how can we do that? Well, since it's larger than 360, we could subtract 360, right? Oh, it's still larger. We can do it again. Okay, so now we know that the sine of 765 is going to be the same as the sine of 45. And then we can go back to this reference angle idea. If you get something like we'll say maybe 180. What can I do to that? Just add 360. That's going to be the same as 180 because 180 minus 360 minus 180 is 180. Now you might think, hey, calculator. I'm not going to take your calculators away for the exam. And assuming you check if you're in the right mode, all might be well. But at some point we're going to use these alternate functions, the inverse functions, and they're going to return to you an angle. And at some point they're going to return an angle, but it's not going to be the right angle. It's not going to be the right angle because these inverse functions have a very limited domain and a limited range. And the answer to your problem may be some number like negative 180. It'll never give that to you. So you do have to understand how this all works. You can't just use the calculator to get by. All right. We've done way too much today. So I'm gonna finish up. We're gonna look at just a little bit more here. What we've done with this section. So far, we've just looked at these two functions, sine and cosine. And you might really think of them as one function, right? If sine of 90 minus theta, the cosine of theta, really that means that these two functions, they're just kind of a shifted and reflection of each other. There, of course, are four more functions, trig functions you have to know about. They don't, they're useful, but they don't really add much. in terms of deep knowledge here. We of course have the tangent, which is defined as the sine over the cosine. Oh, yeah, okay. We also have cotangent, which can be written CTN or COT. Either is fine. That's defined as a reciprocal of the tangent. 1 over the tangent, or maybe preferably cosine of theta over sine of theta. Now, here's something, you wonder why they did this. They could have defined the next two functions either way, but they did it in a way that seems to make it most confusing. There's the secant function, which is 1 over, not the sine, that's the cosine. And the cosecant, which is 1 over the sine. So, you need to remember these. You have to remember that the secant is 1 over the cosine, the cosecant is 1 over the sine. We will look at those functions further when we're going to do some graphing in the next class. I think that's enough. I think I've used enough today. I'm here for a few minutes if you have questions. I know that there are some people here who haven't taken the midterm. Some of those people have told me they're coming after class to take the midterm. And some people haven't responded, but who may come and take the midterm. I hope by the end of office hours, everyone's taking it.